Namaste and welcome back to JEE Chemistry with Typical Monk. This is class 25, Coordination Compounds, part 2. Last class, we named and shaped the complexes. Today we ask why they are colored and magnetic. Two theories answer. Valence bond theory pictures the metal hybridizing its orbitals to grip the ligands and predicts the magnetism. Crystal field theory goes deeper. The ligand's electric field splits the metal's 5D orbitals into two energy levels, and that tiny gap decides the color, the spin, and the stability. Today, valence bond theory, crystal field splitting, the spectrochemical series, and the crystal field stabilization energy, one idea at a time. Here is what you will master today. First, valence bond theory, hybridization and the prediction of magnetism. Second, inner versus outer orbital complexes. Third, crystal field theory and the octahedral splitting. Fourth, the strong versus weak field and the spectrochemical series. And fifth, the crystal field stabilization energy, color, and magnetism. One idea at a time. Let us set the two theories side by side. Two theories. Valence bond theory explains the shape and the magnetism. Crystal field theory explains the color and the splitting. Now, valence bond theory. The metal hybridizes its orbitals to accept a lone pair from each ligand. Crystal field theory. The ligand's field splits the metal's d orbitals into two sets of different energy. Master line. Valence bond theory gives the shape. Crystal field theory gives the color and the finer magnetism. Now look at the picture. The crystal field splitting in an octahedral field. The split. In an octahedral field, the 5d orbitals split into a lower T2 set of 3 and a higher EG set of 2. The gap. The energy difference between them is the crystal field splitting, delta O. The barycenter, the T2 set, drops by 0.4 delta O and the EG set rises by 0.6 delta O, keeping the average energy unchanged. Filling. Electrons fill the T2 set first, but exactly how they fill depends on the size of delta. Now the first theory, valence bond theory. The idea. The metal ion provides empty hybrid orbitals, and each ligand donates a lone pair into one of them. Octahedral. The hybridization is D2sp3. The inner orbital type, or sp32, the outer orbital type. Inner versus outer. A strong ligand forces the electrons to pair and uses the inner d orbitals. A weak ligand uses the outer d orbitals. Magnetism. Count the unpaired electrons after hybridization, and that gives the magnetic moment. Now the idea that ties it all together, the size of the field. Delta O decides. A large delta O from a strong field forces the electrons to pair up in the T2 set. A small delta O from a weak field keeps them apart. Low spin. A strong field gives a low spin complex with fewer unpaired electrons. High spin. A weak field gives a high spin complex with more unpaired electrons. The series. The spectrochemical series ranks the ligands by field strength. Iodide and bromide are weak. Carbonyl and cyanide are strong. The rule. A ligand's place in the series decides whether the complex is high spin or low spin. Now look at the picture. The splitting inner tetrahedral field. Inverted. In a tetrahedral field, the split is reversed, the E set is lower, and the T2 set is higher. Smaller gap. The tetrahedral splitting, delta T, is only about 4/9 of delta O. Always high spin. Because delta T is so small, tetrahedral complexes are almost always high spin. Compare. The octahedral field puts T2G below EG. The tetrahedral field puts E below T2. Now what the splitting gives us: stabilization, color, and magnetism. The crystal field stabilization energy. It is the net drop in energy that comes from filling the split orbitals. Color. A d electron absorbs a photon of energy, delta O, and jumps from the T2Z set to the EG set. And the complementary color is what we see. A bigger delta O. A stronger field means a larger delta O, and so a higher energy, shorter wavelength absorption. Magnetism. The number of unpaired electrons sets the paramagnetism. The moment is mu equals the square root of n times n plus 2. The link, both the color and the magnetism flow from the size of the splitting. Now, the 1 mark facts. Octahedral. The T2 set is below the EG set, low spin for a strong field, high spin for a weak field. Tetrahedral. The E set is below the T2 set, delta T is smaller, so the complexes are almost always high spin. Color and spin. The color comes from a D to D transition of energy delta, O, and the magnetism from the unpaired electrons. Now match each term to its meaning. The hybridisation D2sp3 goes to an inner orbital octahedral complex in valence bond theory. Delta O goes to the octahedral splitting. A strong field ligand goes to a low spin complex. And delta T equal to 4/9 of delta O goes to the tetrahedral field. 4 pairs, each worth memorizing. Now, how many of these statements are correct? Statement 1. A strong field ligand gives a low spin complex. Correct. Statement 2. Tetrahedral complexes are usually low spin. Wrong. They are almost always high spin because delta T is so small. Statement 3. The color comes from a D to D transition of energy delta. Correct. So the answer 2 are correct, statements 1 and 3. The trap is the low spin tetrahedral in statement 2. Now the 2 mistakes that quietly cost marks. The truth: a strong field gives a large delta O and a low spin complex. The trap: assuming that tetrahedral complexes can be low spin, the delta T is simply too small. The second truth: the color arises from a D to D transition with an energy equal to delta. The second trap: inverting the octahedral order. Remember, T2G is lower and EG is higher. Now, test yourself. Answer in your head before the reveal. That is how G speed is built. Here we go. Question 1. In an octahedral field, which set is lower? The T2G. Question 2. A strong field ligand gives which spin? Low spin. Question 3. The tetrahedral splitting compared to the octahedral? About 4/9. Question 4. The color comes from a transition of what energy? Delta O. And question 5. D inner orbital octahedral hybridisation? D2sp3. Let us gather it all in one breath. Valence bond theory, D2sp3 inner or sp32 outer for an octahedral complex. It predicts the shape and the magnetism. Crystal field theory, an octahedral field splits the d orbitals into the T2 set, lower, and the EG set, higher, with a gap of delta O. Spin. A strong field, a large delta O, low spin. A weak field, a small delta O, high spin. The spectrochemical series ranks the ligands from weak to strong. Tetrahedral. The E set below the T2 set. Delta T about 4/9 of delta O, almost always high spin. Next class, organic chemistry, nomenclature and isomerism. 2 theories, 1 prize. Valence bond theory hybridizes the metal and counts the unpaired spins. Crystal field theory splits the d orbitals into T2, JAS and EG. And from that single gap, delta O, comes everything. The spin, the stabilization energy, and the very color of the complex. Learn the octahedral and tetrahedral splittings, the spectrochemical series, and the strong versus weak field rule, and coordination chemistry finally makes sense. Next class, the vast world of carbon, organic chemistry. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time. You will crack JEE. I will see you in the next class.